So this semester, you guys are all looking at machining and metrology. We're going to start out with the metrology side of things, the measurement side of things, looking at doing measurement conversions. Now, we've done some basic measurement conversions before, things like 8 feet going into inches. Now, most of you have done enough measurement that you can just look at that and know what do you have to do to make that conversion. Not divide, but multiply by 12, yeah. 8 feet times 12 is 96 inches. But that's actually kind of a shortcut. What's really going on there is we're using a conversion factor. And that conversion factor takes the form of something mathematically that's called a unity fraction. Now that word isn't necessarily important to you guys, but its function is. A unity fraction is what we use when we're dealing with just regular fractions. Let's say if we have 3/4 and we need to turn it into 20ths. What did we do to that fraction? Well, what do you multiply 4 by to turn it into 20? 5. So we have to multiply the 3 by 5 as well. 3 times 5 is 15. 15 20ths has exactly the same value as 3/4. The reason why is because we multiplied by 5 over 5. 5 over 5, of course, equals 1. That's the definition of a unity fraction. It equals 1. The numerator has the same value as the denominator. Now, when it comes to measurement, the unity fractions don't look as obvious, but for doing 8 feet into inches, it would look like this. We make the 8 feet into a fraction by putting it over 1. And we're going to multiply by, just like we multiplied by 5 over 5 to change the fraction, we're going to multiply by a unity fraction. The units in our unity fraction are determined by the conversion. There's feet here. We're trying to get rid of feet, so I'm going to put feet on bottom. Remember, when you multiply fractions, you can cross-cancel diagonally. That's what this is for. Those feet are going to cancel out. And the relationship between feet and inches is 1 foot equals how many inches? 12 inches. So 12 inches goes on top. Now, at first glance, this does not look like it equals 1, but if you look closer, it does. Because 12 inches and 1 foot are the same value. So it's still equal to 1. So when we multiply by it, it'll change the appearance of our number, but not the value. So 8 times 12 inches is 96 inches. 1 times 1 is 1, so 96 over 1, that's just 96 inches. Well, we got that up here by doing the shortcut, which is fine. For those measurements that we're familiar with, doing that shortcut is okay. But we're going to run into measurements that you might not be familiar with, like this. Too crowded up here. Anyway, you might have 99 feet and be asked to convert it into rods. You guys familiar with rods at all? Rods is basically, it's a measurement of length used for surveying property mostly. Most of your property surveys are done in rods and chains. So a rod is 16.5 or 16.5 feet. So if I'm going from 19 or 99 feet into rods, this is one we're not familiar with, so we don't know just off the top of our head, do you multiply or divide or whatever. But if we set it up, it's going to just lead us right through it. 99 feet over 1. In the other fraction, where does the feet have to go? On bottom, so they cancel out. The relationship, 1 rod is 16.5 feet. So 16.5 feet is 1 rod. The feet are going to cancel out, as we said. On top, we have 99 times 1 rod, which is 99 rods. On bottom, 1 times 16.5 is 16.5. Now up here it was over 1, so we didn't have to do anything. Down here, it's 99 rods over 16.5. So we have to go ahead and divide that out. 99 rods divided by 16.5 is 6 rods. Perfect. Now for this class, we're going to assume that you can do conversions within the standard system. We're going to assume you can do conversions within the metric system. We will do a quick review here, just a couple minutes of the metric system. For length at least. The main unit of length in the metric system is the meter. That is the only unit of length in the metric system. I don't have my meter stick with me. I left it in my classroom, but the meter stick is about 3.4 inches longer than a yard. One of the complaints that I always hear is, why didn't they just make it equal a yard? Well, the problem was they did. A yard is not a uniform unit of measurement. A yard is actually from the center of your nose to the end of your outstretched hand. Well, throughout history, different kings or rulers in different areas declared their yard to be the official yard of the land. So from one area to the next, it was different. They developed the metric system in the late 1800s in Switzerland. The metric meter is equivalent to the Swiss yard, which is apparently their ruler had a little bit longer arms than the English ruler at the time when we established ours. So the meter is a yard, just not the yard we use in this country. That is the only unit of length in the metric system. Anything smaller or longer uses prefixes. So if you recall, as we go smaller, we had deci, which is 1/10. So dm is a decimeter or a tenth of a meter. Of course, m is just a meter. Centi was 100th. So cm was 100th of a meter. Milli was 1,000th. So mm was a millimeter or 1,000th of a meter. Going shorter, they didn't continue to go by tens. They skipped 10,000 and 100,000. And they went to a millionth, which was micro. Now, technically, the scientific abbreviation for micro looks like that. It's the Greek letter mu. It's like a U with a funny tail on it, or an open top P, however you want to look at it. So technically, the abbreviation for micrometer is mu-m, like that. A lot of fields, because you have to keyboard things into a computer, and mu is not a key on the computer, use MCM for micrometer. So if you ever see MCM, that's most likely what they're referring to. The only other thing it could possibly refer to is if they're looking at Roman numerals. They might have MCM. You'll see MCM followed by other letters a lot, because that's MCM is 1900. So that'd be your 1980 whatever dates. Getting larger than a meter. Deca meant 10. Now dm was for decimeter. They used dA for deca, so dam for decameter. Hecto was 100. So hm was a hectometer, was 100 meters. Kilo is 1,000. So km is 1,000 meters, or kilometer. Once again, they skipped 10,000 and 100,000, went up to 1 million. 1 million is mega. Now they used little m for milli, so they use capital M for mega. So capital M, little m is a megameter. 1 million meters or 1,000 kilometers is big. There's only, 25,000 kilometers around the Earth's equator. So there'll only be 25 megameters. So it's really too big to be used. We don't ever really see that. I also don't really ever see hecto and deca used in application, or deci. For most metric units, it's the main unit that gets used. Kilo and milli get used. For length, the centimeter gets used a lot just because it's the closest thing to the inch, and the inch is pretty ingrained in American industry. So the centimeter gets used a lot in the United States. You get over to Europe and they do millimeters way more. Bless you. The conversions in the metric system are relatively straightforward. If I have 4.2 millimeters and I want to convert it to centimeters. Well, if we have this chart down, it's right in the chart. I am going from millimeters to centimeters. So on the chart, from millimeters to centimeters is one spot to the left. All you do is take your decimal point, move over one spot to the left, 0.42 centimeters. The reason that is possible is because each spot on that chart is either multiplying by 10 or dividing by 10. When you multiply or divide by 10, you just move the decimal point one spot. So 290 centimeters going into meters. So we're going from centimeters to meters. Here's centimeters, there's meters. We're moving 2 spots to the left. Now in the 290, there isn't a decimal point written, so that means it's at the end. So we go 2 spots to the left, 2.9. If I have 0.37 meters going into millimeters, going from meters to millimeters, so I'm going from here down to here. I'm moving 1, 2, 3 spots to the right. I move my decimal point 1, 2. I run out of digits, so I have to add a 0 to go 3 spots to the right. That's 370 millimeters. Anybody have any major questions about basic metric conversions? So it does get a little more complex then as we move up into more complex units, like units of area. This type of conversion catches a lot of people off guard because you see feet and inches and you want to just multiply by 12. Why would that not work here? It's square feet and square inches. 1 square foot is defined to be a square that's 1 foot by 1 foot. Well, we know 1 foot is 12 inches, so this is 12 inches by 12 inches. Well, the area of that square, length times width, 12 inches times 12 inches is going to be 144 square inches. So 1 square foot is 144 square inches. So to do this conversion, we put the 3 square feet over 1. Square feet have to go where in my unity fraction? On bottom, so we can get rid of them. Going into square inches, 1 square foot is 144 square inches. The square feet cancel out. I have 3 times 144 is 432 square inches. On bottom, 1 times 1 is 1, so that is just 432 square inches. So how about this one? 108 square feet going into square yards. So we'll start out with our square feet over 1. Of course, square feet have to go on bottom in our unity fraction, and we're converting to square yards. 1 yard is how many feet? 3. So 1 square yard would be how many square feet? 9. 3 by 3. Just like we had 12 by 12 for square inches to square feet, it's 3 by 3 for square feet to square yards. So 3 by 3 is 9. 1 square yard is 9 square feet. So the square feet cancel out. 108 times 1 square yard is 108 square yards. 1 times 9 is 9. And then we just have to divide. 108 divided by 9 is 12. So it's 12 square yards. In the metric system, I'll put my chart back up here again. We're not going to deal with square micrometers or square megameters. We'll just deal with the main 7 units in the center here. If I have 0.42 meters going to centimeters. Now this is just linear meters and centimeters. When I say linear, I'm just saying regular length units of meters and centimeters. Going from meters to centimeters is 2 spots to the right. The decimal point would move 2 spots to the right, 42 centimeters. But if that were 0.42 square meters going into square centimeters, the reason we could just move the decimal point in our regular metric conversion was because, as we said, each spot on the chart is either multiplying by 10 or dividing by 10. If it's square units, though, each spot on the chart is now multiplying by 10 squared, or 100, or dividing by 10 squared, which is 100. If you're multiplying or dividing by 100, the decimal point moves 2 spots. So when it's square units, you have to double the number of places your decimal point moves. So on the chart, from meters to centimeters is 2 spots. But since it's squared units, it's meters squared to centimeters squared, the decimal has to move 4 spots. So I'll write it down here so we've got room to move it. We move 1, 2. We have to add a 0 to go 3 and another 0 to go 4. That's 4,200 centimeters squared. .580 millimeters squared going into centimeters squared. So again, we're going from millimeters to centimeters on the chart. That's 1 spot to the left. Since it's squared units, though, each spot is 2 decimal places. So the decimal point goes 1, 2 spots to the left, 5.8. If you haven't started to get familiar with the metric system, you're a lot like I was so ingrained in customary measurement that the metric system just seemed like pointless. But once you get into it further and further, it is so much easier to use once you get used to it. This is just one of them. I mean, you just double the number of decimal places you move the decimal point instead of having to square the conversion factor. 144 or 12 squared to get 144 and all that. Especially when we get to the next step, which is volume. If I have 3,456 cubic inches, that sounds like a lot of cubic inches, doesn't it? But if I convert that into cubic feet, 1 cubic foot, just like a square foot was defined to be a square that's 1 foot by 1 foot, 1 cubic foot is defined to be a cube that is 1 foot by 1 foot by 1 foot, which means it's 12 inches by 12 inches by 12 inches. So that 1 cubic foot, 12 inches times 12 inches times 12 inches is, you got it, 1,728 cubic inches. So if I go back to converting my 3,456 cubic inches, put 3,456 cubic inches over 1, in my conversion factor, cubic inches go on bottom so that they cancel out. Cubic feet will go on top so I can convert to it. 1 cubic foot is 1728 cubic inches. Cubic inches cancel out. On top, we have 3,456 times 1 cubic foot, which is 3,456 cubic feet. On bottom, 1 times 1728 is 1728. And of course, we have to divide that out. 3,456 divided by 1728 gives us 2 cubic feet. So 3,456 cubic inches sounds like a lot. It's only 2 cubic feet. The more common one that has to be done, this one I used to do quite a bit. Let's see here. Let's do 864 cubic feet going into cubic yards. Can anybody guess why this is such an important conversion? Concrete's the big application here. All your concrete is ordered in cubic. They call it just yards, but it's a cubic yard. So if you're calculating what you need, you calculate it out in cubic feet, and then you have to do that conversion. Well, just like 1 cubic foot was 12 by 12 by 12 inches, or 1728, 1 cubic yard is 3 feet by 3 feet by 3 feet, or 27 cubic feet. So we have our 864 cubic feet over 1. In the conversion factor, cubic feet have to go on bottom again. Cubic yards will be on top. 1 cubic foot is 27 cubic yards. Or sorry, 1 cubic yard is 27 cubic feet. I should say that right. The cubic feet cancel out. 864 times 1 cubic yard is 864 cubic yards. 1 times 27 on bottom is just 27, and we divide to get 32. Back to our metric system again. So again, one movement on the chart of the metric system, if we're talking about length, is multiplying or dividing by 10. So that's moving the decimal point 1 spot. Something like 0.038 meters going into centimeters. Meters to centimeters was 2 spots to the right. The decimal point moved 2 spots to the right, 3.8. If it was a unit of area, 0.038 meters squared, going into centimeters squared, now each spot on the chart was 2 decimal places. Meters to centimeters is still 2 spots to the right. The decimal point has to go 4. 1, 2, 3. We had a 0 to go 4. That's 380 centimeters squared. If it's units of volume, 0.038 meters cubed into centimeters cubed. Now each spot on the chart is 10 by 10 by 10, or 1,000, multiplying or dividing by 1,000. When you multiply or divide by 1,000, the decimal point moves 3 spots. So each spot on the chart is 3 decimal places. So from meters to centimeters is still 2 spots on the chart. The decimal point has to go 6. 1, 2, 3. We fill in zeros to go 4, 5, and 6. That is 38,000 centimeters cubed. You can see how those numbers blow up, get really large in a hurry. If I have 590 cubic millimeters going into cubic centimeters, from millimeters to centimeters, let's get back here. There we go. From millimeters to centimeters is one spot to the left. But since it's cubic millimeters and cubic centimeters, the decimal has to go 3. Right? So the decimal point's right there. It has to go 1, 2, 3. That is 0.59 cubic centimeters. Any questions there so far? With the metric? Yeah. So basically what it is, you're just looking at the power on the units. So here, going from meters to centimeters, it's 2 spots on the chart. Since there's no number there, the decimal just goes 2 spots. When it's squared, 2 spots on the chart, you multiply it by 2 to make it 4 spots because of the 2. When it's cubed, there's a 3 there, 2 spots on the chart, you multiply it by 3 to go 6 spots. So whatever the power is on your units, you multiply the spots on the chart by that power. That's one of those mistakes that I see made. I used to be an engineer before I came here to teach. I saw engineers make that mistake all the time, even with square feet and square inches, cubic feet, cubic inches, of forgetting that you have to change the units when it's volume and area. So be patient with yourself on that one. You bet. So the next step is to look at compound units. Now, there are units of weight and capacity and stuff like that we're going to be throwing in here. We're going to assume you have some sort of familiarity with the standard or customary units. The metric units are going to follow the same chart, so we'll hit those when we need to. One of the things we want to do is convert between customary and metric. So if I have something that's measured as 80 centimeters, and I have a tape measure that only measures in inches, and I want to know how many inches that's going to be. Well, we need to look up somewhere the relationship between inches and centimeters. We're probably going to find the relationship 1 inch is 2.54 centimeters. So this is why I did that conversion factor for converting even with units like feet and inches where we knew what to do. Because here we need that conversion factor to go between measuring systems. So we put our 80 centimeters over 1. In our conversion factor, what's going to go where? Centimeters on bottom, so they cancel out. Good. Then what else? 1 inch on top. 2.54 goes with the centimeters on bottom. So now the centimeters cancel out. Then we multiply straight across. 80 times 1 inch is 80 inches. 1 times 2.54 is 2.54 on bottom. And of course, we need to divide that out. So we do the 80 divided by 2.54. We get 31.50496, depending on where you are on around. We'll go 496. 31.496 inches out of that 80 centimeters. Let's say we have something that is rated with a mass of 120 kilograms. And of course, our rigging is rated in pounds. So we need to make that conversion so we know if our rigging can handle it. The most common conversion used for pounds to kilograms is that 1 kilogram is about 2.2 pounds. It's actually like 2.208 or something like that. So we do our 120 kilograms over 1. And our conversion factor, what's going to go where? Pounds on top. And kilograms on bottom. So 1 goes with the kilograms, 2.2 goes with pounds. Kilograms cancel out. 120 times 2.2 pounds, is that 264 pounds? 1 times 1 is 1, so that's just 264 pounds. If you have a unit that is saying that you need 60 liters of fluid, but your supplier sells in gallons, you might look up that 1 gallon is 3.785 liters. Put our 60 liters over 1. What's going to go in our conversion factor again? Liters go on bottom. So, oops, move that over. The 3.785 liters goes on bottom. The 1 gallon will go on top. Liters cancel out. 60 times 1 gallon is 60 gallons. And 1 times 3.785 is 3.785. And we have to divide that out. 60 divided by 3.785 is about 15.85 gallons. So you're going to have to buy 16 gallons worth of fluid. Any questions there so far? So the nice thing about the conversion factor is you don't have to memorize a bunch of methods of converting. You just have to be able to look up the relationship between the two measurements. If you haven't done it, Google has a great little converter. I hate telling people to just Google it, but this is one of those spots where it's really worth it. So if you just go into Google and type feet to meters, it'll usually pull up this same little chart here where you can come over here and you can select what units you want on this side. If I'm going from feet into meters, 1 foot is 0.3048. Or if you wanted to put the meters here and feet over there, 1 meter is 3.28 feet. It's great about giving you that conversion. Okay. Now we're ready to get to the fun part. I always get nervous when the math teacher says it's going to get fun, right? So let's throw in a challenge here. If I were to tell all of you that I could throw a baseball at a rate of 90 feet per second, would you believe me? No? Oh, thank you. You try again next minute. No, just kidding. Is that fast? And it sounds fast, but is it really? What units are we used to seeing speed in? Miles per hour. So we would want to convert this into miles per hour. So first thing to convert this, we have to recognize that 90 feet per second is actually a rate or a ratio of 90 feet over 1 second. Anytime we have two units like that, or even if it's written out as feet per second, miles per hour, miles per gallon, It is actually a ratio comparing one unit to the other. The 1 is taken out just to shorten it up, but that is 90 feet for every 1 second. Now we have 2 units to convert. We'll start with the numerator in the units, the top unit, which is the feet going to miles. Well, this one we know how to do. We'll put feet on bottom so they cancel out. Miles on top. Anybody remember how many feet are in a mile? You can look it up when the time comes if you need to. 5,280 feet in a mile. So the feet are canceled out. We have miles on top, which is what we want in our final unit. We want to get rid of the seconds. Now here's where things change just a little bit. Seconds are on bottom, so to cancel them out, we have to put them on top. Now we don't necessarily have a direct conversion from seconds into hours. So we might go from seconds into minutes first. The relationship there, which one's bigger, a second or a minute? Minute. So 1 minute equals how many seconds? 60. So now the seconds do cancel out, but we have minutes, and we don't want minutes. So to get rid of minutes, where am I going to put them in my conversion factor? On top. And now we can go to hours, and of course that relationship is 1 hour is 60 minutes. So the minutes cancel out now. Now we have miles on top and hours on bottom, which is what we want in our final unit. So on top, we would take 90 times 1 mile times 60 times 60. What is that? 324,000 miles. On bottom, we have 1 times 5,280 times 1 times 1 hour. That's 5,280 hours. And now we do have to divide this out to make it back into what we call a unit rate. So 324,000 divided by 5,280, was that 61.36? I believe. I'll double check it. Cool. Having a good day today. And then, of course, the units just get put into that rate. Miles divided by hours is miles per hour. So that's 61.36 miles per hour. To be honest, I don't know if I could still throw that fast. 5 years ago, I maybe could, but I'm getting older. So these types of conversions can be made a lot. You might have 0.32 ounces per square inch. We need to know what that is in pounds per square feet. So once again, the 0.32 ounces per square inch becomes 0.32 ounces over 1 square inch. Now, it doesn't matter whether you get rid of the ounces first or the square inches first. I'm used to just starting with whatever unit's on top and changing that one first. So to get rid of ounces, where am I going to put it in the conversion factor? On bottom. We're changing it to what? Pounds. Ounces were on top. Pounds are what we want on top. The relationship? 1 pound equals 16 ounces, yes. So the ounces will cancel out. That'll put us in pounds per square inch. Next, we want to get rid of square inches. Where do we put that in our conversion factor to get rid of it? On top, because it's starting out on bottom. And we're changing square inches into square feet. What's that relationship? I heard somebody mumble it there. 144, there we go. 1 square foot is 144 square inches. So the square inches cancel out. We now have pounds on top, square feet on bottom, which is what we want. So on top, 0.32 times 1 pound times 144 is 46.08. That's pounds. On bottom, 1 times 16 times 1 square foot is 16 square feet. And we have to divide that out. So 46.08 divided by 16 is 2.88. And of course, the units, it was pounds divided by square feet. So that's pounds per square foot. Any questions there? I'm seeing some glazed looks starting. So interrupt me if you need me to slow down or repeat anything. We might have, like wood is approximately 65. When you tip that up, I thought it looked like a whiskey bottle for a second. It's like, share. Well, I can't argue with that. More your dense lumber is about 65 pounds per square foot. If we're dealing with a smaller piece, we might need to define this. Or per cubic foot. If we have a smaller piece, we might need to define this in pounds per cubic inch. Now here, notice only one of the units are changing. The pounds are staying the same. We have the 65 pounds per cubic foot is just 65 pounds over 1 cubic foot. We don't need to change the pounds. We only have to change the cubic feet. So cubic feet is going to go on top. So cubic inches on bottom. And that relationship, if you don't remember the number, you just do 12 times 12 times 12. 1,728. So now the cubic feet cancel out. 65 pounds times 1 is 65 pounds. 1 times 1728 is 1,728 cubic inches. And we have to divide. 65 divided by 1728 is 0.038. Of course, the units will be pounds per cubic inch. When we throw in metric units, it can simplify things or it can make it more complicated. One of the problems that we have is there is no metric unit for time. So if there's time involved, like meters per second or kilometers per hour, we have to deal with the time just like we would with our customary units. So let's say we have a maximum speed that you want a conveyor to operate at of 30 kilometers per hour. Well, that's not a very practical way of measuring the speed of a conveyor. We would probably want that measured in meters per second. So once again, 30 kilometers per hour is 30 kilometers over 1 hour. We have to change kilometers into meters. We could use a conversion factor if we wanted to. Putting kilometers on bottom, meters on top. Which one's longer, a kilometer or a meter? Kilometer. And a kilometer contains 1,000 meters. If you don't remember that, you can go back to the chart. Meters, decameters, hectometers, kilometers. You start with the biggest one, 1 kilometer. You move 1, 2, 3 spots to the right to get to meters. So that decimal moves over 3 spots to make it 1,000 meters. 1 kilometer is 1,000 meters. So the kilometers cancel out. We have meters. Now let's get rid of the hours. I'm going to go ahead and go straight from hours to seconds here because it does happen enough Technically, we should go from hours to minutes, minutes to seconds. But there's 60 minutes in an hour, 60 seconds in a minute. 60 times 60 is 3,600. 3,600 seconds in an hour. The hours cancel out. And then we're going to multiply. On top, 30 times 1,000 meters times 1 is 30,000 meters. On bottom, 1 times 3,600 seconds is 3,600 seconds. So 30,000 divided by 3,600 is 8.33 meters per second. Any questions there? So let's look at the fun ones. 8.2 grams per cubic centimeter going into kilograms per cubic meter. So again, 8.2 grams per cubic centimeter is going to be 8.2 grams over 1 cubic centimeter. We need to come up with conversion factors to convert these. And we could look at our chart. So grams and meters are both going to be in the center of the chart. This would be decigrams, decimeters, centigrams, centimeters, milligrams, millimeters. Going this way, decagrams, decameters, hectograms, hectometers, kilograms, and kilometers. We have to change the grams to kilograms. Which one is larger, a gram or a kilogram? Kilogram. So we start with 1 kilogram. Figure out how many grams it is. From kilograms to grams is 1, 2, 3 spots to the right. Moving that decimal over 3 spots would give us 1,000 grams. We also need to figure out cubic centimeters to meters, to cubic meters. Centimeters and meters, which one's larger? A meter. But we are dealing with cubic meters, so it's 1 cubic meter. Going to cubic centimeters. Meters to centimeters is 2 spots to the right. But since it's cubed, it's 2 times 3, which is 6. So going over 6 spots, that's 1 million cubic centimeters. So now I can use those to do my conversions. To get rid of grams, I'll put grams, 1,000 grams on bottom to 1 kilogram. Grams have canceled out. To get rid of the centimeters cubed, I put my centimeters cubed, 1 million centimeters cubed on top, over my 1 meter cubed on bottom, and the centimeters cubed cancel out. Now there's going to be some big multiplication here. 8.2 times 1 kilogram times 1 million is 8,200,000 kilograms. On bottom, 1 times 1,000 times 1 cubic meter is 1,000 cubic meters. Dividing that out, that's 8,200 kilograms per cubic meter. That's a lot. That's not a very realistic number, by the way. Now, I wanted to show you that way before I showed you this next thing. There is a shortcut when we're dealing with both units being metric. Taking my 8.2 grams over 1 cubic centimeter. Rather than doing the conversion factors like we did here, which I think is the safest way of doing it, but if you start to get comfortable with metric units, you can just move the decimal points. I can turn my grams into kilograms. That was 3 spots to the left on the chart. My decimal point has to go 3 spots to the left. Filling in zeros, that would be 0.0082 kilograms. Centimeters cubed to meters cubed. Centimeters to meters is 2 spots on the chart. Cubed means we go times 3, so 2 times 3 is 6 decimal places. Our decimal point has to go 1, 2, 3, 4, 5, 6. That's 0.000001 cubic meters. Then you divide those numbers out to 82,000, and it's kilograms over meters cubed, or cubic meters. This way is a lot shorter and quicker if you can make it work for you. That doesn't work for everybody, but I showed it, put it out there as a shortcut for some of you. Okay, let's take a quick break. Let's take about 10 minutes. We'll be back here about 10:34. Yep. Okay, so the next step. We talked a little, I mentioned a little bit about some of the convenience of the metric system, and this is going to illustrate part of it. Going between different units. Within the customary system, there is no neat conversion. Even just between capacity and volume, which really measure the same thing. Both are measuring how much stuff is inside something. There isn't a neat conversion. Like 1 gallon isn't even exact. It's approximately 231 cubic inches. So if I want to know how many gallons are in this tank here that has interior dimensions of 30 inches by 25 inches by 20 inches, I'll find that volume. (30 inches times 25 inches times 20 inches, which gives us, what, 1,500 cubic inches? But now I have to convert that into gallons. So I'll put my 1,500 cubic inches over 1, and I go through the conversion factor. Cubic inches on bottom, 231 cubic inches is approximately 1 gallon. And the cubic inches will cancel out. 1,500 times 1 gallon is 1,500 gallons. And on bottom, 1 times 231 is 231. And of course, we need to divide that out. So 1,500 divided by 231 gives us 6.49 gallons approximately. That's about 6.5 gallons. Whereas in the metric system, that's a pretty simple conversion, because in the metric system, they defined 1 milliliter to be equivalent to 1 cubic centimeter. So if I have a tank let's say that this is 90 centimeters by 60 centimeters by 50 centimeters. I find its volume by doing 90 centimeters times 60 centimeters times 50 centimeters. What do we get there? 270,000 cubic centimeters. If I want that in milliliters, since 1 milliliter is 1 cubic centimeter, that's 270,000 milliliters. And of course, I can convert it to liters from there by just moving the decimal points. But I want to go one more step. The metric system makes it even more convenient by defining 1 gram is equal to the mass of 1 milliliter of water. So if I want to know how heavy this tank is, each milliliter is 1 gram. So if it's going to be filled with water, 270 milliliters is going to be 270 grams. And of course, I can move the decimal point from grams to kilograms as 3 to the right, or 3 to the left, sorry. That'll be 270 kilograms. So the metric system has those very convenient, neat conversions from one unit to the other as well. Whereas in the standard system, customary system, it's like 8.32 pounds per gallon if you're dealing with standard fluids. Okay. Our last unit conversion we want to talk about before we get more into the precision measurement is temperature conversion. In the customary system, of course, we deal with degrees Fahrenheit. The benchmarks we typically use are where water freezes and where water boils. In our customary system, what temperature does water freeze? 32 degrees Fahrenheit. Anybody remember what temperature water boils? 212. Good. 212 degrees Fahrenheit. In the metric system, they use degrees Celsius. At what temperature does water freeze in degrees Celsius? 0. And boils? 100. So a couple of things to point out here. One is, in the Celsius scale, there's 100 degrees between freezing and boiling. Because of this, the Celsius scale is sometimes referred to as the centigrade scale. Centi meaning 100, grade divisions. There's 100 divisions between freezing and boiling. In the Fahrenheit scale, there's 180 degrees between water freezing and water boiling, which means the size of 1 degree Fahrenheit is smaller than 1 degree Celsius. It takes more of them to get the same distance. But more significant here is the fact that there is no common 0 point. What does that mean? Well, for length, 0 feet is 0 meters. For weight or mass, 0 kilograms is 0 pounds. For capacity, 0 liters is 0 gallons. 0 is 0 in most of those units. For temperature, however, 0 Celsius is 32 degrees Fahrenheit. They don't have a common 0 point, which means we can't just use a simple conversion factor to get from one to the other. We have to use a formula. So if I'm going from degrees Fahrenheit into degrees Celsius, I take my Fahrenheit temperature, and the first thing I have to do is subtract my difference in freezing temperatures. 32 and 0, I subtract 32 degrees. Next, I have to account for the difference in the size of 1 degree. That's ratio is 180 to 100. 100 over 180, if I reduce that fraction, both 100 and 180 divided by 20 to give me 5 over 9. So it's 5/9 times that difference after I've subtracted the 32 degrees. That'll give me my degrees Celsius. Let's look at a standard one. Let's look at body temperature. 98.6 degrees Fahrenheit. Let's convert that into degrees Celsius. So the 98.6 goes in where F is here. Have to remember order of operations. What do we do first here? Parentheses, we're going to subtract. 98.6 minus 32 is 66.6. Now we've reduced the parentheses to a single number. We can get rid of the parentheses, but we have to remember that is still indicating multiplication there. 5/9 times 66.6 is 37. So it's 37 degrees Celsius. So human body temperature is 37 degrees Celsius. Going the other direction from degrees Celsius into degrees Fahrenheit. We reverse the process. We start with the Celsius temperature, and to account for the difference in the size of a degree, we multiply by 9/5. Instead of 5/9, we're going the other way. We multiply by 9/5. And then after we've multiplied, we add on the 32-degree difference. So let's say you're driving into work and you hear the weatherman say it's going to be 20 degrees Celsius today. Is that going to be a nice day? Well, let's plug it in. So here we're going to put 20 in where C is. Remember, 9/5 C means 9/5 times C, or times 20, plus the 32. Order of operations, what do we have to do first there? Multiply 9/5 by 20, which is 36. And then we just add those two numbers. 36 plus 32 is 68 degrees Fahrenheit. That's a pretty nice day in my book. Any questions on those formulas? So I'll scroll back up to make sure you have those two formulas down if you need them. So next on our list, we're going to talk about some precision measurement. Hopefully we can move through this rather quickly. I'm hoping you guys all have some experience with calipers and micrometers. Just doing a quick review to make sure that we're on the same page. So precision measurement, we're going to start out with dial calipers. Does anybody in here still use vernier calipers for any of their stuff? Good. They've kind of been pushed out of use and for good reason. They were a very good tool. At one point, the gearing for the dial calipers was sloppy, so they were very inaccurate. But we've become more precise with creating our gears and stuff, so the dial calipers are within about 5/10 thousandths of an inch usually. It's not worth the trouble of reading a vernier scale when you're that close. So just a quick thing, dial calipers can actually be used to measure in 4 different ways. Most people are only familiar with the first way, which is inside the big jaws, measuring the outside of an object like that. But there's also the secondary jaws on the back. Anybody ever use those? Yep. It's for measuring inside. When this is closed, those jaws line up, so you can use it to measure the inside of a hole like that. Those are the two that most people are familiar with. This one is the one that usually catches people. It's called a step measurement. When the jaws are closed, this top edge of that jaw usually lines up exactly with the top edge of the main jaw. So as you open the jaws up, the distance between them is the same as the distance between the big jaws. So you can use it like this to measure the step up between two surfaces. Anybody ever do that one? That's the one that most people have never seen. And then the last one, of course, is the depth measurement, which is one that you almost have to have a caliper set aside for that, because that little strip of metal that sticks out always gets bent, and I've clipped it off of a few of mine because they get bent up to the point where they don't slide in and out. For measuring depths with that little depth gauge. Okay, so from there, let's look at reading. I'll blow that up a little bit bigger for you. Our calipers. So this is an inch caliper. You can tell because it says inch in the middle there. But also because on the main scale here, we have 2 sets of numbers. You can see we got the bigger set 0, 1, and then we got the 1 through 9 in between them. First thing you have to do with a caliper is figure out what your reference edge is. To do that, you would close the jaws, and when the jaws are closed, you'd see what lines up with 0. For this caliper, it's this little notch right here. How many of you have read standard calipers before? Good, so we can get through this relatively quickly. So on the main scale, you get two numbers, whole inches and tenths. So on the main scale, how many whole inches do we have? 1. How many tenths? 3. Perfect. So it's 1.3, and then on the dial, that lines up with 52. So 1.352 inches is what that's reading. How about this one? Main scale is 1 point. That's the same one. I don't know why I put that. Oh, I did it to blow it up. That's why. Here, this one. Now here, on the main scale, that's 1 whole inch. Are we at the 0.9 yet? No, because if we look at the dial is not quite back to 0, which means we have not made it to the next line. So we're not at the 9 yet. That's 1.8, and then the dial reads 9.4. So 1.894 inches. We'll read one more. What's this one read? .404. Perfect. It is just past 0, so that means we did pass the 0.4. And, of course, the 4 is in the thousands place. Let's skip ahead to metric. This is the vernier, by the way. I don't think you guys need to know the vernier. Anybody curious to see how it works? Not really. So you read the main scale where the 0 is. So this would be 0.6 inches. And then you do have quarter marks there. We're not past any of those. So it's just 0.600. Then you look to see which one of these lines lines up. It looks like it's, well, there's 3 of them that look like 16, 17, and 18. All 3 look like they line up. That's just because there's only so many pixels on the computer screen. We'll take the middle one, 17. So that's 0.617 inches is what that's reading. The vernier scale, just the lines are slightly closer. So however far you are past the reading with the 0, that's which line will line up for you on the next scale. I'm not going to stress the vernier scale, partly for time, partly because on a computer screen, they're really rough to read. In real life, every time I've had to use one, I always tilt them so I can see right down the lines. You can see exactly which ones line up. Here, this is metric. For this one, you have to be a little careful because this one, it is 1 centimeter, but the dial is in millimeters. So you have to read that as 10 millimeters. This would be 20 millimeters. So this is 21 millimeters. 21 point, what's the dial reading? 5.2, so 21.52 millimeters. So what's this one reading? What's on the main scale here? 37.86 millimeters. We'll do one more. What's this one reading? 59.91. Perfect. Any question on the metric calipers? I do have more examples if you need to see more. Vernier metric is similar, only this is labeled from 0 through 10. Notice only every 2 spots, it's only 5 spots between 0 and 1. So each spot on here is actually 2. So this is 2, 4, 6, 8, 10 is what those are reading. So this is 43 point. Not seeing which ones line up. There. Yeah, I was gonna say it looks like those 3 all line. Those like 5 of them all line up. So I'd do like 0.48 maybe. It looks to be about the middle one. That was one of the problems with the vernier is there's 2 or 3 lines that line up. You just have to pick one. Usually it's 3 lines. You pick the middle one, but sometimes there's some guesswork involved in it. Yeah, we don't need to do mixed practice. Let's jump to the micrometer. So this is a standard micrometer. Zoom out just a touch. You can tell because, well, it goes up to 20 and then back to 0 there. Also, this is labeled by 1s here on the barrel of the micrometer. Micrometers are usually 0 to 1 inch. They only have 1 inch of travel because there's 40 threads per inch, which means you have to spin the thimble 40 times to move it 1 inch. So if you're going from like 0 to 3 inches, that's a lot of spinning if you're adjusting it all the way out. So if you need to measure something bigger than an inch, they have some that when they're closed, they only close down to an inch and they go from 1 inch to 2 inches. The biggest I've seen, I think I saw a 7 to 8 inch is the largest one I've seen, but I've had people tell me they've seen bigger micrometers. Anyway, so the main scale here, this is 0.2, but then we have quarter marks here. So this is 25, 50, 75. We read that main scale at the edge of the thimble here. Then we read the thimble where the axis of the main scale, the axis of the barrel lines up. That is between 11 and 12. It's closer to 12. So that is 12 thousandths. So that is 0.287 inches is what that's reading. How about this one? So off the barrel, the main scale, how many tenths? 0.3. We're at the 25. Have we made it past the 50? No, we're not quite back to 0 yet. So we're at the 25. Then on the thimble, what are we reading? 23, I'd say. Yeah. 0.023. So that is 0.348 inches. I'll give you a minute to read this one on your own. What are you getting? 0.40, 401, 402, either one I would accept. That one's almost exactly right in the middle, isn't it? 4015. There's a good point. Can we say 4015 since it's right in the middle? No. If we say that, then you're implying that your measuring device went to the 10,000th of an inch, and it doesn't. So it's really tempting to fill those in, but we can't do it. We don't want to do the vernier. Let's skip to metric. So in the metric, you can tell this is metric because this goes above 20. It doesn't go back. It goes all the way up to 45 and then back to 0. And the main scale on the barrel is labeled in 5s. So this is 5 millimeters. This is 6 millimeters. Down here, these are half marks. So this is 0, 1/2, 1, 1.5, 2, 2.5, 3, and on up like that. So this is saying 6.5 or 6.5. Then we read the thimble again where that axis of the barrel is. That would be at 19. That's 1900ths. So that's 6.69 millimeters is what that is reading. So for this one, what are we reading off the barrel here, off the main scale? 7, and we're not past any half marks. That's 7.0. What are we reading over here on the thimble? 9. That's 900ths, so that's 7.09 millimeters. I'll give you a minute to read this one on your own, then we'll put it together here. So what's that reading? 10.08. You got it. Any questions on inch or millimeter micrometers? Okay. We're going to call it good for those. Now the next measuring device we want to look at is scales with gauges. I know you've all read gauges, so we're going to go through this pretty quickly again. Our only purpose here is to get good at figuring out scales. So the gauge I like to use for figuring out scales is this one here. The reason I like it is because it has 3 different scales on one gauge, and sometimes it's a little tricky to figure out what each marking stands for. And that's really the key to reading any gauge, is figuring out what the markings stand for. So the first thing here, since there's 3 sets of numbers, we have to figure out what set of numbers. This dial down here is at the 16, which means we're going to use the middle set. So the 10, 11, 12, 13, 14, 15. This little line here is indicating where the needle is pointing. To figure out what that is, we need to know what each of those spaces indicates. So we're going, this line is at 12, this line is at 13, that is 1 volt. How many spaces are in between there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Divide by 10 spaces, that is 0.1 volt for each space. So this is 12, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. That one's fairly simple because each line is 0.1 volt. But when we get to this one, it gets a little more complex. We're on the 8 here, which means we're going to read the smaller set of numbers, the top set. So there, from 6 to 7, there is 1 volt. How many spaces? Well, 1, 2, 3, 4, 5 spaces. To here, I know each of those is 5 spaces, so this will be 10, 15, and 20. I don't want to have to count up all that way. So that's 20 spaces. 1 volt divided by 20 spaces is 0.05 volts per space. So here, this is 7 volts. This is actually 7.05. A lot of people mistakenly read that as 7.1. You have to make sure you take the time to figure out what the spacing is. And then this one, it's on the 24, which means we're reading bottom set, the big numbers. So here, this is 22, this is 24. That's a difference of 2 volts. There's 5, 10 spaces. So each space is 0.2 volts. So this is 22, 22.2, 22.4, 22.6. So for this one, I'm going to put it on the 24 volt setting. And my needle is going to be put right there. I'll give you a minute to read that, and then we'll see what you got. What's it read? 27.2 volts. Good. Then I'll put you on this setting, and we're going to put it, slide it up a little. Let's put it right here. I'll give you a second to read that, then we'll go over it. What's that reading? Perfect. 6.4. So this is 6. It's 0.05 per mark. So 0.05, 10, 15, 20, 25, 30, 35, 40. 6.40. Any questions there? So then, of course, some of them just have a little bit different scale. This one's fairly simple to read. What's that indicating there? 37, yes. Each line is just 1 unit. Here's one we don't see much anymore. This is a logarithmic scale for resistance. So you can see here, What a space on the scale means is different from where we're at. This is 1 ohm here. About that same distance up here is 10 ohms. So you almost have to look at where it is and kind of count between numbers. Like we have the 7 and the 10 marked here. What's that arrow pointing at? Yeah, it's pointing at the 8, and somebody caught the 1,000 there on the dial. 8,000 is what that's reading. Yeah, we don't need to read a lot more of those. That's good for those. The final gauge I want to get at is a surface gauge. And only because a surface gauge is got several parts to reading it. So a surface gauge, sometimes called a surface deviation gauge or just a dial indicator. This is used for leveling surfaces or detecting whether a surface is flat, deviations within a flat surface. So here, these gauges set on a surface, and sometimes they have a magnetic thing, otherwise it's just a pressure set. You get them adjusted so they're set at 0, but they can either be pushed in to go up, or you can move out and they'll extend out and they'll go negative in the opposite direction. So the first thing you have to read on these gauges is whether it's going in the positive or negative direction. Well, usually you would watch the needle as it moved to see what direction it moved. Here there's an arrow. So this arrow is telling you that this moved in the positive direction. The second thing is these gauges can go around multiple times. So you have to look at the small dial here to see if we've made more than one revolution. It's between 0 and 1, which means we haven't. So it's 0 full revolutions. And then the needle is at what there? 17. So that is a positive 0.17 millimeters. This one, positive or negative? Negative. Any full millimeters on the little dial? It's between 2 and 3, so that's 2. Good. And now be careful reading this. I'll tell you up front, that's not 19. 81. Good. We're going this way. 10, 20, 30, 40, 50, 60, 70, 80, 81. How many of you have used this type of an indicator? You have. We'll just do a couple more examples and then we'll move on for you. So here, positive or negative? Negative. Whole millimeters? No. And on the dial? 29. Good. Last one, then we'll go to inch. Oh, that one's, let's do this. This is my blank one, so I can do extra practice. Pretend that line's straight. So, positive or negative? Negative whole millimeters? 3 and 63. Perfect. So for the inch indicator, it's the same, just the decimal points moved over. Positive or negative? Positive. Now this is not whole inches anymore, it's tenths of an inch. So that is 0.1 and then 10. You got it. So this one, positive or negative? Negative. Point. Are we at the 9? No, we're not quite back to 0. We're going that direction. We're not quite back to 0, so we're not quite to the 9 yet. That's 0.8. 78. Perfect. Any questions on those? Cool. It's always fun to hit a part that you guys already know, so I don't have to do too much with it. So the next section, dealing with measurement. So on a blueprint or drawing, you see this labeled 3.650 inches plus or minus 0.015 inches. What does that mean? You're allowed variation one way or another. This number is what we call the desired value, sometimes called the ideal value, because in an ideal world, that's what we would want it to be. But since the world is not ideal, we're allowed to vary a little bit on each side. Now, a lot of people refer to this number as a tolerance. Its technical name is allowance. We're allowed to be that far on each side. This implies a range. That acceptable range would be the desired value minus the allowance. So 3.650 minus the 15 thousandths would be 3.635 inches, to the desired value plus the allowance, hence the plus or minus. So that's 3.665 inches. Anything between those measurements is acceptable. Now you might see a measurement labeled .400 inches plus or minus 0.5%. So this is what is referred to as a relative allowance. Well, this one up here was an absolute allowance. Sometimes called absolute tolerance and relative tolerance. The reason is this allowance here is absolute. It's 15 thousandths no matter what the size of this measurement is. Here it's relative. It's 0.5% of whatever. The bigger this measurement is, the bigger the allowance is going to be because of that percent. So we need to go back to our percent calculations to figure out the absolute size of the allowance here. Remember, a percent is always over 100. So 0.5% is 0.5 over 100. We need to figure out how much that is out of 2.4 inches. To find the missing number in the proportion, we cross multiply and divide. So it is 0.5 times 2.4 divided by 100. We get 0.012. So this is the same as saying 2.00 or 2.40 inches plus or minus 0.012 inches. What does this mean? We can be under, but we cannot be over. So it's saying is we really want it to be 2.875, but if we can't be exactly that, we want to make sure we're smaller than it, not bigger. So it's going to give us a range again, 2.875 minus the 0.010, which is 2.865 inches, to, well, 2.875 plus 0.000 is just 2.875. So we get that range. Well, that is the same range we would have if I listed this as 2.870 inches plus or minus 5 thousandths of an inch. We'd get the exact same range. So why would we list it like this rather than this? Preference? Oh, partly. We're looking at what we really need the part to be. This is telling us we really do want the part to be 2.875 if possible. This is saying we really want it to be 2.870, we can be bigger or smaller. So the difference would be is, let's say you have a machine that you're going to be producing this if you're repairing or replacing a piece, and your machine is capable to being plus or minus 0.003 of an inch. Well, if it's listed like this, you're just going to set the machine to 2.870 inches, knowing that the plus or minus 0.003 is going to put you within that range, right? You're shooting towards the middle. But if it's listed like this, it's telling you we'd rather have it towards the top end. You're going to set your machine at 2.872, knowing that the plus or minus 3 is still going to keep you in that range, but we're getting closer to the bigger side where we really want it to be. Does that make sense? The last step would be, let's say that we have a part that has to be between 1.667 inches to 1.695 inches. We don't want to list it like that on a drawing, so we want to convert this to be a desired value plus or minus an allowance. How do we find the desired value? Well, if this is a bilateral allowance, so it's the same on either side, plus or minus, we know the desired value is going to be right between those numbers, right? How do we find a number that's right between them? We could do that, subtract, divide by 2, and then add it on. Or we can just add them together and divide the total by 2. 1.667 plus 1.695. Now be very careful on your calculator when you do this. Hit equals first before you divide by 2. Otherwise, it'll give you some really strange answer. So 1.681 is right in the middle. To find the allowance, the plus or minus, we do have to do what you were saying before. Subtract them. 1.695 minus 1.667 and divide it by 2. Oops, get back here. So 1.695 minus 1.667. Once again, you hit equals before you divide by 2. This is saying that that's 0.014, so plus or minus 0.014 inches. Now, what you were saying, you could actually find this number first, which is what you would have found, and then go back and subtract it from the large value would have given you the 1.681. So there are a couple of different ways you could go about finding the desired value and allowance from this. Any questions? Well, I usually like to give you a few minutes to start on your worksheet. Unfortunately, today I only gave you very few, but we'll get the worksheet out to you. Oh, you can do it.
First after the semester.
So for those of you that are new, what we do is we're going to have you over the next couple of weeks work on this worksheet. When we come back in 2 weeks, I'll have another 2 hours like this. We'll go over the worksheet together, make sure everybody has it down. And then there will be a quiz that will be just on the material of the worksheet. And then we'll do the second part of class, which we'll do a little bit of basic trig and stuff. And we're going to hack trig down because we don't have time to define all the functions and all that. Just functional trig. How do you find different pieces out of it? That stuff will be on the quiz. You'll have a worksheet, but not just like the worksheet quiz. It's not too high pressure. And the good news is even if you totally drop this, it's only like 4%. Okay. for those of you that are new, I should put this up there. If you need to contact me, my email address is todd.hoff@northwoodtech.edu. This is recorded. I haven't shut it off yet. Once I shut off the recording, I will start processing it. I'll probably get it posted by the end of the day Tuesday. I probably won't get it done over the weekend with the holiday weekend. But if you email me sometime next week, I can send you the link to that video. So if you want to go back and look through the video, you can do that. Or if you have any other questions, those of you that are new, if you want any of those review resources that I mentioned, let me know and I can send some of those to you as well if you feel like there's some things you want to brush up on before we go any further.
Still on the YouTube channel?
Yeah.